Earth is the third planet from the Sun and the only astronomical object known to harbor life. While million, excuse me, while large volumes of water can be found throughout the solar system, only Earth sustains liquid surface water. About 71% of Earth's surface is made up of the ocean, dwarfing Earth's polar ice, lakes, and rivers. The remaining 29% of Earth's surface is land, consisting of continents and islands. Earth's surface layer is formed of several slowly moving tectonic plates interacting to produce mountain ranges, volcanoes, and earthquakes. Earth's liquid outer core generates a magnetic field that shapes Earth's magnetosphere, deflecting destructive solar winds. Earth's atmosphere consists mostly of nitrogen and oxygen. More solar energy is received by tropical regions than polar regions and is redistributed by atmospheric and oceanic circulation. Water vapor is widely present in the atmosphere and forms clouds that cover most of the planet. Greenhouse gases in the atmosphere, like carbon dioxide, trap a part of the energy from the sun close to the surface. A region's climate is governed by latitude, but also by elevation and proximity to moderating oceans. Severe weather, such as tropical cyclones, thunderstorms, and heat waves, occurs in most areas and greatly impacts life. Earth is an ellipsoid with a circumference of about 40,000 kilometers. It is the densest planet in the solar system. Of the four rocky planets, it is the largest and most massive. Earth is about 8 light minutes away from the Sun and orbits it, taking a year, about 365.25 days, to complete one revolution. Earth rotates around its own axis in slightly less than a day, in about 23 hours and 56 minutes. Earth's axis of rotation is tilted with respect to the perpendicular to its orbital plane around the Sun, producing seasons. Earth is orbited by one permanent natural satellite, the Moon, which orbits Earth at 380,000 kilometers, or 1.3 light seconds, and is roughly a quarter as wide as Earth. The Moon always faces the Earth with the same side through tidal locking and causes tides, stabilizes Earth's axis, and gradually slows its rotation. Earth formed over 4.5 billion years ago. During the first billion years of Earth's history, the ocean formed and then life developed within it. Life spread globally and began to affect Earth's atmosphere and surface, leading to Earth's great oxidation event 2 billion years ago. Humans emerged 300,000 years ago and have reached a population of almost 8 billion today. Humans depend on Earth's biosphere and natural resources for their survival, but have increasingly impacted Earth's climate. Today, humanity's impact on Earth's climate, soils, waters, and ecosystems is unsustainable, threatening people's lives and causing widespread extinction of other life. Hmm. The modern English word, excuse me. The modern English word earth developed via Middle English from an Old English noun most often spelled Jesus Christ. Most often spelled erod. It has cognates in every Germanic language, and their ancestral root has been reconstructed as Erthel, I think. In its earliest attestation, the word Eroth was, I guess, was already being used to translate the many senses of Latin terra and Greek ge. Guy? Eh? The ground, its soil, dry land, the human world, the surface of the worlds, including the seas and the globe itself. As with the Roman terra telus and Greek Gaia, Earth may have been a personified goddess in German paganism. Late Norse mythology included Joro, Earth, as a gigantus, often given as the mother of Thor. Historically, Earth has been written in lower case, from early Middle English to its definite sense as the globe was expressed as the Earth. By the era of early modern English, capitalization of nouns began to prevail, and the Earth was also written as the Earth, particularly when referenced along with other heavenly bodies. More recently, the name is sometimes given simply as Earth, by analogy with the names of other planets. Although Earth and forms of the remain common, house styles now vary. Oxford spelling recognizes the lowercase form as the most common, with the capitalized form an acceptable variant. Another convention capitalizes Earth when appearing as a name, for example, Earth's atmosphere, but writes it in lowercase when preceded by the, for example, the atmosphere of the Earth. It almost always appears in lowercase in colloquial expressions such as, "What on earth are you doing?" Occasionally, the name Terra is used in scientific writing and especially in science fiction to distinguish humanity's inhabited planet from others, while in poetry, Tellus has been used to denote personification of the Earth. Terra is also the name of the planet in some Romance languages, languages that evolved from Latin, like Italian and Portuguese, while in other Romance languages the word gave rise to names with slightly altered spellings, like the Spanish tierra and the French terre. The Latinate form Gaia, or Gaia, of the Greek poetic name Gaia, is rare, although the alternative spelling Gaia has become common due to the Gaia hypothesis, in which case its pronunciation is Gaia rather than more classical English Gaia. There are a number of adjectives for planet Earth. From Earth itself becomes earthly. From the Latin terra comes terran, terrestrial, and via French, terrain. And from the Latin tellus comes Tellurian and Telluric. The oldest material found in the solar system is dated to 4.5 billion years ago. By 4.54 gigaannum, the primordial Earth had formed. The bodies in the solar system formed and evolved with the Sun. In theory, a solar nebula partitions a volume out of molecular cloud by gravitational collapse, which begins to spin and flatten to a circumstellar disk. And then the planets grow out of that disk with the Sun. A nebula contains gas, ice grains, and dust, including primordial nuclides. According to nebular theory, planetesimals formed by accretion, with the primordial Earth being estimated as likely taking anywhere from 70 to 100 million years to form. Estimates of the age of the moon range from 4.5 gigaannum to significantly younger. Excuse me. A leading hypothesis is that it was formed by accretion from material loose from Earth after a Mars-sized object with about 10% of Earth's mass, named Theia, collided with Earth. It hit Earth with a glancing blow when some of its mass merged with Earth. Between approximately 4.1 and 3.8 gigaannum, numerous asteroid impacts during the late heavy bombardment caused significant changes to the greater surface environment of the moon and, by inference, that of Earth. Earth's atmosphere and oceans were formed by volcanic activity and outgassing. Water vapor from these sources condensed into the oceans, augmented by water and ice from asteroids, protoplanets, and comets. Sufficient water to fill the oceans may have been on Earth since it formed. In this model, atmospheric greenhouse gases kept the oceans from freezing, where the newly forming sun had only 70% of its current lumosity. By 3.5 gigaannum, Earth's magnetic field was established, which helped prevent the atmosphere being stripped away by the solar wind. Here we see an artist's impression of Earth during the Archean Eon, showing falling meteor, erupting volcano, round stromatolites, and barren landscape. As the molten outer layer of Earth cooled, it formed the first solid crust, which is thought to have been mafic in composition. The first continental crust, which was more felsic in composition, formed by the partial melting of the mafic crust. The presence of grains in the mineral zircon of Hadean age in Archean sedimentary rocks suggests that at least some felsic crust existed as early as 4.4 gigaannum, only 140 megaannum after Earth's formation. There are two main models of how the initial small volume of continental crust evolved to reach its current abundance. One, a relatively steady growth up to the present day, which is supported by the radiometric volume of continental crust, evolved to reach its current abundance. Shit. Excuse me. Okay, let me try that one again. One, relatively steady growth up to the present day, which is supported by the radiometric dating of continental crust globally, and two, an initial rapid growth in the volume of continental crust during the Archean, forming the bulk of the continental crust that now exists, which is supported by isotopic evidence from hafnium in zircons and mm, neodymium one more time, which is supported by isotopic evidence from hafnium in zircons and neodymium in sedimentary rocks. The two models and the data that support them can be reconciled by large-scale recycling of the continental crust, particularly during the early stages of Earth's history. Here we see a planetary disk around the sun-like star TW Hydrae. The inner ring has a radius equal to the distance from the sun to Earth, suggesting an infant version of Earth could be emerging from the dust and gas. The other concentric light and dark features represent other planet-forming regions further out in the disk. New continental crust forms as a result of plate tectonics, a process ultimately driven by the continuous loss of heat from Earth's interior. Over the period of hundreds of millions of years, tectonic forces have caused areas of continental crust to group together to form supercontinents that have subsequently broken apart. At approximately 750 megaannum, one of the earliest known supercontinents, Rodinia, began to break apart. The continents later recombined to form Pannotia at 600 to 540 megaannum, then finally Pangaea, which also began to break apart at 180 megaannum. The most recent pattern of ice ages began around 40 megaannum, and then intensified during the Pleistocene about 3 megaannum. High and middle latitude regions have since undergone repeated cycles of glaciation and thaw, repeating about every 21,000, 41,000, and 100,000 years. The last glacial period, colloquially called the Last Ice Age, covered large parts of the continents, up to the middle latitudes in ice, and ended around 11,700 years ago. Chemical reactions led to the first self-replicating molecules about 4 billion years ago. A half-billion years later, the last common ancestor of all current life arose. The evolution of photosynthesis allowed the sun's energy to be harvested directly by life forms. The resultant molecular oxygen, accumulated in the atmosphere and due to interaction with ultraviolet solar radiation, formed a protective ozone layer in the upper atmosphere. Excuse me. The incorporation of smaller cells within larger ones resulted in the development of complex cells called eukaryotes. True multicellular organisms formed as cells within colonies became increasingly specialized. Aided by the absorption of harmful ultraviolet radiation by the ozone layer, life colonized Earth's surface. Among the earliest fossil evidence for life is microbial mat fossils found 3.48 billion year old sandstone in Western Australia. Biogenic graphite found in 3.7 billion year old metasedimentary rocks in western Greenland, and remains of biotic material found in 4.1 billion year old rocks in western Australia. The earliest direct evidence of life on Earth is contained in 3.45 billion year old Australian rocks showing fossils of microorganisms. During the Neoproterozoic, one more time. During the Neoproterozoic 1000 to 539 megaannum, much of Earth might have been covered in ice. This hypothesis has been termed snowball Earth and is of particular interest because it preceded the Cambrian explosion, when multicellular life forms significantly increased in complexity. Following the Cambrian explosion, 535 megaannum, there have been at least 5 major mass extinctions and many minor ones. Apart from the proposed current Holocene extinction event, the most recent was 66 megaannum, when an asteroid impact triggered the extinction of the non-avian dinosaurs and other large reptiles, but largely spared small animals such as insects, mammals, lizards, and birds. Mammalian life has diversified over the past 66 million years, and several million years ago, an African ape gained the ability to stand upright. This facilitated tool use and encouraged communication that provided the nutrition and stimulation needed for a larger brain, which led to the evolution of humans. The development of agriculture and then civilization led to humans having an influence on Earth and the nature and quantity of other life forms that continues to this day. Because carbon dioxide has a long lifespan in the atmosphere, moderate human carbon dioxide emissions may postpone the next glacial inception by 100,000 years. Earth's expected long term future is tied to that of the Sun. Over the next 1.1 billion years, solar luminosity will increase by 10%, and over the next 3.5 billion years by 40%. Earth's increasing surface temperature will accelerate the inorganic carbon cycle, reducing carbon dioxide concentration to levels lethally low for plants, 10 parts per million for C4 photosynthesis, in approximately 100 to 900 million years. The lack of vegetation will result in the loss of oxygen in the atmosphere, making animal life impossible. Due to the increased luminosity, Earth's mean temperature may reach 100 degrees Celsius or 212 degrees Fahrenheit in 1.5 billion years, and all ocean water will evaporate and be lost to space, which may trigger a runaway greenhouse effect with an estimated 1.623 billion years. Even if the sun were stable, a fraction of the water in the modern oceans will descend to the mantle due to reduced steam venting from mid ocean ridges. The sun will evolve to become a red giant in about 5 billion years. Models predict that the sun will expand to roughly 1 AU, 150 million kilometers or 93 million miles, about 250 times its present radius. Earth's fate is less clear. As a red giant, the sun will lose roughly 30% of its mass, so without tidal effects, Earth will move to an orbit of 1.7 AU, or 250 million kilometers, or 160 million miles, from the Sun, where the star reaches its maximum radius. Otherwise, with tidal effects, it may enter the Sun's atmosphere and be vaporized. The shape of Earth is nearly spherical. There is a small flattening at the poles and bulging around the equator due to Earth's rotation. Therefore, a better approximation of Earth's shape is an oblate spheroid, whose equatorial diameter is 53 kilometers larger than the pole to pole diameter. The average diameter of the reference spheroid is 12,000 kilometers or 7,900 miles. Local topography deviates from this idealized spheroid, although on a global scale these deviations are small compared to Earth's radius. The maximum deviation of only 0.17% is at the Mariana Trench of 10,000 meters or 35,000 feet below local sea level, whereas Mount Everest, 8,800 meters or 29,000 feet above local sea level, represents a deviation of 0.14%. The point on the surface farthest from the Earth's center of mass is the summit of the equatorial Chimborazo volcano in Ecuador, 6,300 kilometers or 3,900 miles. In geodesy, the exact shape of Earth's oceans would adopt in the absence of land, and perturbation such as tides and winds is called the geoid. More precisely, the geoid is the surface of gravitational equipotential at mean sea level, or MSL. Ocean surface topography are water deviations from MSL analogous to land topography. Here we see Earth's topographical map. The area is redder if it is raised higher in real life. Earth's interior, like that of the other terrestrial planets, is divided into layers by their chemical or physical, rheological properties. The outer layer is a chemically distinct silicate solid crust, which is underlain by a highly viscous solid mantle. The crust is separated from the mantle by the Moravic discontinuity. The thickness of the crust varies from about 6 kilometers or 3.7 miles under the oceans to 30 to 50 kilometers or 19.31 miles for the continents. The crust and the cold, rigid top of the upper mantle are collectively known as the lithosphere, which is divided into independently moving tectonic plates. Beneath the lithosphere is the asthenosphere, a relatively low viscosity layer on which the lithosphere rides. Important changes in crystal structure within the mantle occur at 410 and 660 kilometers, or 250 and 410 miles below the surface, spanning a transition zone that separates the upper and lower mantle. Beneath the mantle, an extremely low viscosity liquid outer core lies above a solid inner core. Earth's inner core may be rotating at a slightly higher angular velocity than the remainder of the planet, advancing by zero point 0.1 to zero point 0.5 degrees per year, although both somewhat higher and much slower rates have also been proposed. The radius of the inner core is about one-fifth of that of Earth. Density increases with depth as described in the table on the right. Earth's mass is approximately 5.97 times 10 to the 24 kilograms, or 5,900 YG. Not sure what that measurement is. It is composed mostly of iron, 32.1%, oxygen, 30.1%, silicon, 15.1%, magnesium, 13.9%, sulfur, 2.9%, nickel, 1.8%, calcium, 1.5%, and aluminum, 1.4%, with the remaining 1.2% consisting of trace amounts of other elements. Due to mass segregation, the core region is estimated to be primarily composed of iron, 88.8%, with smaller amounts of nickel, 5.8%, sulfur, 4.5%, and less than 1% trace elements. The most common rock constituents of the crust are nearly all oxides. Chlorine, sulfur, and fluorine are the important exceptions to this, and their total amount in any rock is usually much less than 1%. Over 99% of the crust is composed of 11 oxides, principally silica, alumina, iron oxides, lime, magnesia, potash, and soda. The major heat producing isotopes within Earth are potassium 40, uranium 238, and thorium 232. At the center, the temperature may be up to 6,000 degrees Celsius or 10,000 degrees Fahrenheit, and the pressure could reach 360 gigapascals or 52 million psi. Because much of the heat is provided by radioactive decay, scientists postulate that early in Earth's history, before isotopes with short half lives were depleted, Earth's heat production was much higher. At approximately 3 GYR, twice the present day heat would have been produced, increasing the rates of mantle convection and plate tectonics, and allowing the production of uncommon igneous rock such as comatolites that are rarely formed today. Billion years ago. Yeah, 3 billion years ago. The mean heat loss from Earth is 87 megawatts. M to the meter. Minute? Milliwatt? That's a weird notation. Okay. The mean heat loss from Earth is 87 MWM to the negative 2 for a global heat loss of 4.42 times 10 to the 13th watts. A portion of the core's thermal energy is transported toward the crust by mantle plumes, a form of convection consisting of upwellings of higher temperature rock. These plumes can produce hot spots and flood basalts. More of the heat in Earth is lost through plate tectonics by mantle upwelling associated with mid-ocean ridges. The final major mode of heat loss is through conduction through the lithosphere, the majority of which occurs under the oceans because the crust there is much thinner than that of the continents. Earth's mechanically rigid outer layer, the lithosphere, is divided into tectonic plates. These plates are rigid segments that move relative to each other at one of three boundary types. At convergent boundaries, two plates come together. At divergent boundaries, two plates are pulled apart. And at transform boundaries, two plates slide past one another laterally. Along these plate boundaries, earthquakes, volcanic activity, mountain building, and oceanic transformation can occur. The tectonic plates are on top of the asthenosphere, the solid but less viscous part of the upper mantle that can flow and move along with the plates. Right here. Here we see the global map of heat flow from Earth's interior to the surface. As the tectonic plates migrate, oceanic crust is subducted under the leading edges of the plates at convergent boundaries. At the same time, the upwelling of mantle material at divergent boundaries creates mid-ocean ridges. The combination of these processes recycles the oceanic crust back into the mantle. Due to this recycling, most of the ocean floor is less than 100 megaannum old. The oldest oceanic crust is located in the Western Pacific and is estimated to be 200 megaannum old. By comparison, the oldest dated continental crust is 4,000 megaannum, although zircons have been found preserved as clasts within Archean sedimentary rocks that give ages up to 4,400 megaannum, indicating that at least some continental crust existed at that time. Here we see Earth's major plates, which are the Pacific Plate, African Plate, North American Plate, Eurasian Plate, Antarctic Plate, Indo-Australian Plate, and the South American Plate. The seven major plates. The seven major plates are the Pacific, North American, Eurasian, African, Antarctic, Indo-Australian, and South American. Other notable plates include the Arabian Plate, the Caribbean Plate, the Nazca Plate off the west coast of South America, and the Scotia Plate in the southern Atlantic Ocean. The Australian Plate fused with the Indian Plate between 50 and 55 megaannum. The fastest moving plates are the Oceanic Plates, with the Cocos Plate advancing at a rate of 75 millimeters a year, or 3 inches a year, and the Pacific Plate moving 52 to 69 millimeters a year, or 2 to 2.7 inches a year. At the other extreme, the slowest moving plate is the South American Plate, progressing at a typical rate of 10.6 millimeters a year, or 0.42 inches a year. The total surface area of Earth is about 510 million kilometers squared, or 197 million square miles. Of this, 70.8%, or 361.13 million kilometers squared, or 139.43 million square miles, is below sea level and covered by ocean water. Below the ocean surface are much of it the continental shelf, mountains, volcanoes, oceanic trenches, submarine canyons, oceanic plateaus, abyssal plains, and a globe-spanning mid-ocean ridge system. The remaining 29.2%, or 148.9 million kilometers squared, or 57.5 million square miles, not covered by seawater, has terrain that varies greatly from place to place and consists of mountains, deserts, plains, plateaus, and other landforms. The elevation of the land surface varies from the low point of negative 418 meters, or negative 1,300 feet, at the Dead Sea, to a maximum altitude of 8,800 meters, or 29,000 feet, at the top of Mount Everest. The mean height of land above sea level is about 797 meters, or 2,600 feet. Here's the satellite picture of Uppsala Glacier, showing mountains, icebergs, lakes, and clouds. The continental crust consists of lower density material such as igneous rocks, granite, and andesite. Less common is basalt, a denser volcanic rock that is the primary constituent of the ocean floors. Sedimentary rock is formed from the accumulation of sediment that becomes buried and compacted together. Nearly 75% of the continental surfaces are covered by sedimentary rocks, although they form about 5% of the crust. The third form of rock material found on Earth is metamorphic rocks, which is created from the transformation of pre-existing rock types through high pressures, high temperatures, or both. The most abundant silicate minerals on Earth's surface include quartz, feldspars, amphibole, mica, pyroxene, and olivine. Common carbonate materials include calcite, found in limestone, and dolomite. Erosion and tectonics, volcanic eruptions, flooding, weathering, glaciation, the growing of coral reefs, and meteorite impacts are among the processes that constantly reshape Earth's surface over geological time. The pedosphere is the outermost layer of Earth's continental surface and is composed of soil and subject to soil formation processes. The total arable land is 10.9% of the land's surface, with 1.3% being permanent cropland. Close to 40% of Earth's land surface is used for agriculture, or an estimated 16.7 million kilometers squared, or 6.4 million square miles of cropland, and around 33.5 million kilometers squared, 12.9 million square miles of pastureland. The gravity of Earth is the acceleration that is imparted to objects due to the distribution of mass within Earth. Near Earth's surface, gravitational acceleration is approximately 9.8 meters per second squared, or 32 feet per second squared. Local differences in topography, geology, and deeper tectonic structure cause local and broad regional differences in Earth's gravitational field, known as gravity anomalies. The main part of Earth's magnetic field is generated in the core, the site of a dynamo process that converts the kinetic energy of thermally and compositionally driven convection into electrical and magnetic field energy. The field extends outwards from the core, through the mantle and up to Earth's surface, where it is approximately a dipole. The poles of the dipole are located close to Earth's geographic poles. At the equator of the magnetic field strength at the surface is 3.05 times 10 to the negative 5t, with a magnetic dipole moment of 7.79 times 10 to the 22 am squared. At epoch 2000, decreasing nearly 6% per century, although it still remains stronger than its long-time average. The convection movements in the core are chaotic, the magnetic poles drift and periodically change alignment. This causes secular variation of the main field and field reversals at irregular intervals, averaging a few times every million years. The most recent reversal occurred approximately 700,000 years ago. Here you see a schematic of Earth's magnetosphere, with the solar wind flows from left to right. The extent of Earth's magnetic field in space defines the magnetosphere. Ions and electrons of the solar wind are deflected by the magnetosphere. Solar wind pressure compresses the day side of the magnetosphere to about 10 Earth radii, and extends the night side magnetosphere into a long tail. Because the velocity of the solar wind is greater than the speed at which waves propagate through the solar wind, a supersonic bow shock precedes the day side magnetosphere within the solar wind. Charged particles are contained within the magnetosphere. The plasmasphere is defined by low energy particles that essentially follow magnetic field lines as Earth rotates. The ring current is defined by medium energy particles that drift relative to the geomagnetic field, both paths that are still dominated by the magnetic field, and the Van Allen radiation belts are formed by high energy particles whose motion is essentially random but contained in the magnetosphere. During magnetic storms and substorms, charged particles can be deflected from the outer magnetosphere, and especially the magnetotail, directed along field lines into Earth's ionosphere, where atmospheric atoms can be excited and ionized, causing the aurora. Well, that was one hell of a section. Jesus Christ. Lots of long E's. Earth's rotation period relative to the Sun, its mean solar day, is 86,000 seconds of mean solar time, or 86,000 SI seconds, with just a difference of 0.0025. Because Earth's solar day is now slightly longer than it was during the 19th century due to tidal deceleration, each day varies between 0 and 2 milliseconds longer than the mean solar day. Earth's rotation period relative to the fixed stars, called its stellar day by the International Earth Rotation and Reference System Service, or IERS, is 86,164.0989 seconds of mean solar time, UT1, or 23 hours 56 minutes 4.90989 seconds. Earth's rotation period relative to the precessing or moving mean March equinox, when the sun is at 90 degrees on the equator, is 86,164.0905 seconds of mean solar time, UT1, 23 hours 56 minutes 4.0905 seconds. Thus, the sidereal day is shorter than the stellar day by about 8.4 milliseconds. Here we see Earth's rotation by Deep Space Climate Observatory showing axis tilt. Apart from meteors within the atmosphere and low-orbiting satellites, the main apparent motion of celestial bodies in our sky is to the west at a rate of 15 degrees per hour, or 15 minutes per minute. For bodies near the celestial equator, this is equivalent to an apparent diameter of the sun or moon every 2 minutes. From Earth's surface, the apparent sizes of the sun and moon are approximately the same. Earth orbits the sun at an average distance of about 150 million kilometers, or 93 million miles, every 365.2564 mean solar days, or 1 sidereal year. This gives an apparent movement of the sun eastward with respect to the stars at a rate of about 1 degree a day, which is 1 apparent sun or moon diameter every 12 hours. Due to this motion, on average, it takes 24 hours, a solar day, for Earth to complete a full rotation about its axis so that the sun returns to the meridian. The orbital speed of Earth averages about 29.78 kilometers per second, or 107,000 kilometers per hour, 66,000 miles per hour, which is fast enough to travel distance equal to Earth's diameter, about 12,000 kilometers or 7,900 miles, in 7 minutes, and the distance to the Moon, 384,000 kilometers or 239,000 miles, in about 3.5 hours. Here's the illustration of the Earth, Earth's orbit, and the Sun, and the 4 seasons. The Moon and Earth orbit a common barycenter every 27.32 days relative to the background stars. When combined with the Earth-Moon system's common orbit around the Sun, the period of the synodic month from new moon to new moon is 29.53 days. Viewed from the celestial North Pole, the motion of Earth, the Moon, and their axial rotations are all counterclockwise. Viewed from a vantage point above the Earth and Earth's North Poles, Earth's orbits in a counterclockwise direction around the Sun. The orbital and axial planes are not precisely aligned. Earth's axis is tilted some 23.44 degrees from the perpendicular to the Earth-Sun plane, the ecliptic. And the Earth-Moon plane is tilted up to plus minus 5.1 degrees against the Earth-Sun plane. Without this tilt, there would be an eclipse every 2 weeks, alternating between lunar eclipses and solar eclipses. The Hill sphere, or the sphere of gravitational influence of Earth, is about 1.5 million kilometers, or 930,000 miles in radius. This is the maximum distance at which Earth's gravitational influence is stronger than the more distant Sun and planets. Objects must orbit Earth within its radius, or they can become unbound by the gravitational perturbation of the Sun. Earth, along with the solar system, is situated in the Milky Way and orbits around 28,000 light years from its center. It is about 20 light years from the galactic plane of the Orion Arm. The axial tilt of Earth is approximately 23.4 degrees, with the axis of its orbit plane always pointing towards the celestial poles. Yeah, I was not reading all those digits, man. Due to Earth's axial tilt, the amount of sunlight reaching any given point on the surface varies over the course of the year. This causes a seasonal change in climate, with summer in the northern hemisphere occurring when the Tropic of Cancer is facing the sun, and the southern hemisphere when the Tropic of Capricorn faces the sun. In each instance, winter occurs simultaneously in the opposite hemisphere. During the summer, the day lasts longer and the sun climbs higher in the sky. In winter, the climate becomes cooler and the day is shorter. Above the Arctic Circle and below the Antarctic Circle, there is no daylight at all for part of the year, causing a polar night, and this axis extends for several months. And this night extends for several months at the poles themselves. These same latitudes also experience a midnight sun, where the sun remains visible all day. Here we see Earth's axial tilt and its rotation to the in its relation to the rotational axis and planes of orbit. By astronomical convention, the four seasons can be determined by the solstices, the points in the orbit of maximum axial tilt toward or away from the sun, and the equinoxes, when Earth's rotational axis is aligned with its orbital axis. In the northern hemisphere, winter solstice currently occurs around December 21st, summer solstice is near June 21st, spring equinox is around March 20th, and autumnal equinox is around 22nd or 23rd of September. In the southern hemisphere, the situation is reversed, with the summer and winter solstice exchange and the spring and autumnal equinox date swaps. The angle of Earth's axial tilt is relatively stable over long periods of time. Its axial tilt does undergo nutation, a slight irregular motion with a mean period of 18.6 years. The orientation rather than the angle of Earth's axis also changes over time, precessing around in a complete circle over each 25,000-year cycle. This precession is the reason for the difference between the sidereal year and a tropical year. Both of these motions are caused by the varying attraction of the sun and moon on Earth's equatorial bulge. The poles also migrate a few meters across Earth's surface. This polar motion has multiple cyclical components, which collectively are termed quasi-periodic motion. In addition to an annual component to this motion, there is a 14-month cycle called the Chandler wobble. Earth's rotational velocity also varies in a phenomenon known as length of day variation. In modern times, Earth's perihelion occurs around January 3rd and its aphelion around July 4th. These dates change over time due to precession and other orbital factors which follow cyclical patterns known as Milankovitch cycles. The changing Earth-Sun distance causes an increase of about 6.8% in solar energy reaching Earth at perihelion relative to aphelion. Because the southern hemisphere is tilted toward the sun around the same time that Earth reaches the closest approach to the sun, the southern hemisphere receives slightly more energy from the sun than does the northern over the course of the year. This effect is much less significant than the total energy change due to the axial tilt, and most of the excess energy is absorbed by the higher proportion of water in the southern hemisphere. The Moon is a relatively large, terrestrial, planet-like natural satellite with a diameter about 1/4 of Earth's. It is the largest moon in the solar system relative to the size of its planet, although Charon is larger relative to the dwarf planet Pluto. The natural satellites of other planets are also referred to as moons after Earth's. The most widely accepted theory of the moon's origin is the giant impact hypothesis, states that it formed from the collision of a Mars-sized protoplanet called Theia with the early Earth. This hypothesis explains, among other things, the moon's relative lack of iron and volatile elements and the fact that its composition is nearly identical to that of Earth's crust. The gravitational attraction between Earth and the moon causes tides on Earth. The same effect on the moon has led to its tidal locking. Its rotation period is the same as the time it takes to orbit Earth. As a result, it always presents the same face to the planet. As the moon orbits Earth, different parts of its face are illuminated by the sun, leading to the lunar phases. Due to their tidal interaction, the moon recedes from Earth at the rate of approximately 38 millimeters a year, or 1.5 inches a year. Over millions of years, these tiny modifications and the lengthening of Earth's day by about 23 microseconds a year add up to significant changes. During the Ediacaran period, for example, approximately 620 megaannum, there are 400 plus minus 7 days in a year, with each lasting 21.9 plus minus zero point 0.4 hours. Here we see the Earth-Moon system seen from Mars. The moon may have dramatically affected the development of life by moderating the planet's climate. Paleontological evidence and computer simulations show that Earth's axial tilt is stabilized by tidal interactions with the moon. Some theorists think that without the stabilization against the torque supplied by the sun and the planet's Earth's equatorial bulge, the rotational axis might be chaotically unstable, exhibiting large changes over millions of years, as is the case for Mars, though this is disputed. Viewed from Earth, the moon is just far enough away to have almost the same apparent size disk as the sun. The angular size, or solid angle, of these two bodies match because, although the sun's diameter is about 400 times as large as the moon's, it is also 400 times more distant. This allows annular, total and annular solar eclipses to occur on Earth. Earth's co-orbital asteroids population consists of quasi-satellites, objects with a horseshoe orbit, and Trojans. There are at least 5 quasi-satellites, including 469219 Kamo Olewa, a Trojan asteroid companion, 2010 TK7, is librating around the leading Lagrange triangular point, L4, in Earth's orbit around the Sun. The tiny near-Earth asteroid 2006 RH120 makes close approaches to the Earth-Moon system roughly every 20 years. During these approaches, it can orbit Earth for brief periods of time. Excuse me, Jesus. Oh yeah. Oh dear. Oh dear. How am I doing? Here we see the Hubble Space Telescope seen in orbit from the Space Shuttle Atlantis. As of September 2021, there are 4,500 operational human-made satellites orbiting Earth. There are also inoperative satellites, including Vanguard 1, the oldest satellite currently in orbit, and over 16,000 pieces of tracked space debris. Earth's large artificial satellite is the International Space Station. Oh, gee whiz. Earth's... Oh, fuck. Loosen up a little bit. Alright. I think it's... God, tripping over my tongue. Your mouth just gets tired after a while. Alright. Earth's hydrosphere consists chiefly of the oceans, but technically includes all water surfaces in the world, including inland seas, lakes, rivers, and underground waters, down to a depth of 2,000 meters or 6,600 feet. The mass of the oceans is approximately 1.35 times 10 to the 18 metric tons, or about 1 over 4,400 of Earth's total mass. The oceans cover an area of 361.8 million kilometers squared, or 1.39.7 million square miles, with a mean depth of 3,600 meters or 12,000 feet, resulting in an estimated volume of 1.3 billion kilometers cubed, or 320 million cubic miles. If all of Earth's crustal surface were the same elevation as a smooth sphere, the depth of the resulting world ocean would be 2.7 to 2.8 kilometers, or 1.68 to 1.74 miles. About 97.5% of the water is saline, the remaining 2.5% is freshwater. Most freshwater, about 68.7%, is present as ice in ice caps and glaciers. Here we see the process leading to movements and phase changes in Earth's water. In Earth's oldest coldest... Shit. In Earth's coldest... Wow, I can't even say Earth right now. In Earth's coldest regions, snow survives over the summer and changes into ice. This accumulated snow and ice eventually forms into glaciers, bodies of ice that flow under the influence of their own gravity. Alpine glaciers form in mountainous areas, whereas vast ice sheets form over land and polar regions. The flow of glaciers erodes the surface, changing it dramatically, with the formation of U-shaped valleys and other landforms. Sea ice in the Arctic covers an area about as big as the United States, although it is quickly retreating as a consequence of climate change. The average salinity of Earth's oceans is about 35 grams of salt per kilogram of seawater, 3.5% salt. Most of this salt was released from volcanic activity or extracted from cool igneous rocks. The oceans are also a reservoir of dissolved atmospheric gases, which are essential for the survival of many aquatic life forms. Seawater has an important influence on the world's climate, with the oceans acting as a large heat reservoir. Shifts in the oceanic temperature distribution can cause significant weather shifts, such as the El Nino Southern Oscillation. The abundance of water on Earth's surface is a unique feature that distinguishes it from other planets in the solar system. Solar system planets with considerable atmospheres do partly host atmospheric water vapor, but they lack surface conditions for stable surface water. Despite some moons showing signs of large reservoirs of extraterrestrial liquid water, with possibly even more volume than Earth's ocean, all of them are large bodies of water under a kilometer's thick frozen surface layer. Just go. Ugh, God damn, I picked a long article. The atmospheric pressure at Earth's sea level averages 101.3 kilopascals or 14.69 psi, with a scale height of around 8.5 kilometers or 5.3 miles. A dry atmosphere is composed of 78% nitrogen, 20%, 20.9% oxygen, 0.934% argon, and trace amounts of carbon dioxide and other gaseous molecules. Water vapor content varies between 0.01% and 4%, but averages about 1%. The height of the troposphere varies with latitude, ranging from 8 kilometers or 5 miles at the poles to 17 kilometers or 11 miles at the equator, with some variation resulting from weather and seasonal factors. Earth's biosphere has significantly altered its atmosphere. Oxygenetic photosynthesis evolved 2.7 billion years ago, forming the primarily nitrogen oxygen atmosphere of today. This climate enabled the proliferation of aerobic organisms and indirectly the formation of the ozone layer due to the subsequent conversion of atmospheric oxygen into ozone. The ozone layer blocks ultraviolet solar radiation, permitting life on land. Other atmospheric functions important to life include transporting water vapor, providing useful gases, causing small meteors to burn up before they strike the surface, and moderating temperature. The last phenomenon is known as the greenhouse effect. Trace molecules within the atmosphere serve to capture thermal energy emitted from the ground, thereby raising the average temperature. Water vapor, carbon dioxide, methane, nitrous oxide, and ozone are the primary greenhouse gases in the atmosphere. Without this heat retention effect, the average surface temperature would be negative 18 degrees Celsius or 0 degrees Fahrenheit. In contrast to the current plus 15 degrees Celsius or 59 degrees Fahrenheit, and life on Earth probably would not exist in its current form. Excuse me while I text this girl I like. Anyways, where was I? Ah, yes. Earth's atmosphere has no definite boundary, gradually becoming thinner and fading into outer space. Three-quarters of the atmosphere's mass is contained within the first 11 kilometers, or 6.8 miles, of the surface. The lowest layer is called the troposphere. Energy from the sun heats this layer and the surface below, causing expansion of the air. This lower density air then rises and is replaced by excuse me, cooler, higher density air. The result is atmospheric circulation that drives weather and climate change through redistribution of thermal energy. Excuse me. The primary atmospheric circulation bands consist of the trade winds in the equatorial region below 30 degrees latitude and the westerlies in the mid latitudes between 30 degrees and 60 degrees. Ocean heat content and currents are also important factors in determining climate, particularly the thermohaline circulation that distributes thermal energy from the equatorial oceans through the polar oceans regions. You see Hurricane Felix seen from low Earth orbit September 2007, and massive clouds above the Mojave Desert February 2016. Earth receives 1300 watts per meter squared of solar irradiance. The amount of solar energy that reaches the Earth's surface decreases with increasing latitude. At higher latitudes, the sunlight reaches the Earth's surface at lower angles, and it must pass through thicker columns of the atmosphere. As a result, the mean annual air temperature at sea level decreases by about 0.4 degrees Celsius or 0.7 degrees Fahrenheit per degree of latitude from the equator. Earth's surface can be subdivided into specific latitudinal belts of approximately homogeneous climate, ranging from the equator to the polar regions. These are the tropical or equatorial, subtropical, temperate, and polar climates. Further factors that affect a location's climates are its proximity to oceans, the oceanic and atmospheric circulation, and topology. Places close to oceans typically have colder summers and warmer winters due to the fact that oceans can store large amounts of heat. The wind transports the cold or the heat of the ocean to the land. Atmospheric circulation also plays an important role. San Francisco and Washington, D.C. are both coastal cities at about the same latitude. San Francisco's climate is significantly more moderate, as prevailing wind direction is from sea to land. Finally, temperatures decrease with height, causing mountainous areas to be colder than low-lying areas. What do you know? Both my former hometown and my current place of residence are in the same sentence in a Wikipedia article. Look at that. Water vapor generated through surface evaporation is transported by circulatory patterns in the atmosphere. When atmospheric conditions permit an uplift of warm, humid air, this water condenses and falls to the surface as precipitation. Most of the water is then transported to lower elevations by river systems and usually returned to the oceans or deposited into lakes. This water cycle is a vital mechanism for supporting life on land and is a primary factor in the erosion of surface features over geological periods. Precipitation patterns vary widely, ranging from several meters of water per year to less than a millimeter. Atmospheric circulation, topographic features, and temperature differences determine the average precipitation that falls in each region. The commonly used Köppen climate classification system has five broad groups: humid tropics, arid, humid middle latitudes, continental, and cold polar, which are further divided into more specific subtypes. The Köppen climate system rates regions based on observed temperature and precipitation. Surface air temperature can rise to around 55 degrees Celsius or 131 degrees Fahrenheit in hot deserts such as Death Valley, and can fall as low as negative 89 degrees Celsius or negative 108 degrees Fahrenheit in Antarctica. Above the troposphere, the atmosphere is usually divided into the stratosphere, mesosphere, and thermosphere. Each layer has a different lapse rate. defining the rate of change in temperature with height. Beyond these, the exosphere thins out into the magnetosphere, where the geomagnetic fields interact with the solar wind. Within the stratosphere is the ozone layer, a component that partially shields the surface from ultraviolet light, and thus is important for life on Earth. The Kármán line, defined as 100 kilometers 62 miles above Earth's surface, is a working definition for the boundary between the atmosphere and outer space. We see the top of Earth's blue-tinted atmosphere with the moon in the background. Thermal energy causes some of the molecules at the outer edge of the atmosphere to increase their velocity to a point where they can escape from Earth's gravity. This causes a slow but steady loss of atmosphere into space. Because unfixed hydrogen has a low molecular mass, it can achieve escape velocity more readily, as it leaks into outer space at a greater rate than other gases. Leakage of hydrogen into space contributes to the shifting of Earth's atmosphere and surface from an initially reducing state to its current oxidizing one. Photosynthesis provided a source of free oxygen, but the loss of reducing agents such as hydrogen is thought to have been a necessary precondition for the widespread accumulation of oxygen in the atmosphere. Hence, the ability of hydrogen to escape from the atmosphere may have influenced the nature of life that developed on Earth. In the current oxygen-rich atmosphere, most hydrogen is converted into water before it has an opportunity to escape. Instead, most of the hydrogen loss comes from the destruction of methane in the upper atmosphere. A planet's life forms inhabit ecosystems whose total forms of the biosphere. The biosphere is divided into a number of biomes inhabited by broadly similar plants and animals. On land, biomes are separated primarily by differences in latitude, height above sea level, and humidity. Terrestrial biomes, lying within the Arctic or Antarctic circles at high altitudes or in extremely arid areas, are relatively barren of plant and animal life. Species diversity reaches a peak in humid lowlands at equatorial latitudes. Estimates of the number of species on Earth vary. Most species have not been described. Over 99% of all species that ever lived on Earth are extinct. Here we see fungi are one of the kingdoms of life on Earth. A planet that can sustain life is termed habitable, even if life did not originate there. The distance of Earth from the Sun, as well as its orbital eccentricity, rate of rotation, axial tilt, geological history, sustaining atmosphere, and magnetic field all contribute to the current climatic conditions at the surface. Earth provides liquid water, an environment where complex organic molecules can assemble and interact, and sufficient energy can sustain metabolism. Plants can take up nutrients from the atmosphere, soils, and water. These nutrients are constantly recycled between different species. Extreme weather, such as tropical cyclones, including hurricanes and typhoons, occurs over most of Earth's surface and has a large impact on life in those areas. From 1980 to 2000, these events caused an average of 11,000 human deaths per year. Many places are subject to earthquakes, landslides, tsunamis, volcanic eruptions, tornadoes, blizzards, floods, droughts, wildfires, and other calamities and disasters. Human impact is felt in many areas due to pollution of the air and water, acid rain, loss of vegetation, including overgrazing, deforestation, and desertification, loss of wildlife species extinction, soil degradation, soil depletion, and erosion. Human activities release greenhouse gases into the atmosphere, which cause global warming. This is driving changes such as the melting of glaciers and ice sheets, a global rise in average sea levels, increased risk of drought and wildfires, and migration of species to colder areas. Earth's human population passed 7 billion in the early 2010s, and is projected to peak at around 10 billion in the second half of the 21st century. Most of the growth is expected to take place in sub-Saharan Africa. Human population density varies widely around the world, but a majority live in Asia. By 2050, 68% of the world's human population is expected to be living in urban rather than rural areas. The Northern Hemisphere contains 68% of the world's landmass. Partly due to the predominance of landmass, 90% of humans live in the northern hemisphere. Here we see the sovereign states of the world. It is estimated that one-eighth of Earth's surface is suitable for humans to live in. Three-quarters of Earth's surface is covered by oceans, leaving one-quarter as land. Half of that land area is desert, 14%, high mountains, 27%, or other unsuitable terrains. Humans have developed diverse societies and cultures. Politically, the world has about 206 sovereign states. States claim the planet's entire land surface, except for parts of Antarctica and a few other unclaimed areas. Earth never had a planet wide government, but the United Nations is a leading worldwide intergovernmental organization. The first human to orbit Earth was Yuri Gagarin on April 12, 1961. In total, around 550 people have visited outer space and reached orbit as of November 2018, and of these, 12 have walked on the moon. Normally, the only humans in space are those on the International Space Station. The station's crew, made up of 6 people, is usually replaced every 6 months. The farthest that humans have traveled from Earth is 400,000 kilometers or 248,000 miles, achieved during the Apollo 13 mission in 1970. Earth has resources that have been exploited by humans. Those termed non-renewable resources, such as fossil fuels, are only replenished over geological timescales. Large deposits of fossil fuels are obtained from Earth's crust, consisting of coal, petroleum, and natural gas. These deposits are used by humans both for energy production and as feedstock for chemical production. Mineral ore bodies have also been formed within the crust through a process of orogenesis, resulting from actions of magmatism, erosion, and plate tectonics. These metals and other elements are extracted by mining, a process which often brings environmental and health damage. You see Earth's land use for human agriculture. Earth's biosphere produces many useful biological products for humans, including food, wood, pharmaceuticals, oxygen, and the recycling of organic waste. The land-based ecosystem depends upon topsoil and fresh water, and the oceanic ecosystem depends on dissolved nutrients washed down from the land. In 2019, 39 million kilometers squared, or 15 million square miles of Earth's land surface consisted of forests and woodlands. 12 million kilometers squared, or 4.6 million square miles, was shrub and grassland. 40 million kilometers squared, 15 million square miles, was used for animal feed production and grazing. And 11 million kilometers squared, or 4.2 million square miles, were cultivated as croplands. Of the 12 to 14% of ice-free land that is used for croplands, 2 percentage points were irrigated in 2015. Humans use building materials to construct shelters. Excuse me a moment. Human activities have impacted Earth's environments. Through activities such as burning of fossil fuels, humans have been increasing the amount of greenhouse gases in the atmosphere, altering Earth's energy budget and climate. It is estimated that global temperatures in the year 2020 were 1.2 degrees Celsius or 2.2 degrees Fahrenheit warmer than the pre-industrial baseline. This increase in temperature, known as global warming, has contributed to the melting of glaciers, rising sea levels, increased risk of droughts and wildfires, and migration of species to colder areas. The concept of planetary boundaries was introduced to quantify humanity's impact on Earth. Of the 9 identified boundaries, 5 have been crossed: biosphere integrity, climate change, chemical pollution, destruction of wild habitats, and the nitrogen cycle are thought to have passed the safe threshold. As of 2018, no country meets the basic needs of its population without transgressing planetary boundaries. It is, though, possible to provide all basic physical needs globally within sustainable levels of resource use. Here you see the change in average surface air temperature and drivers for that change. Human activity has caused increased temperatures with natural forces adding some variability. Human cultures have developed many views of the planet. The standard astronomical symbols of Earth are a quartered circle, representing the 4 corners of the world, and a globulous cruciger. Earth is sometimes personified as a deity. In many cultures, it is a mother goddess that is also the primary fertility deity. Creation myths in many regions involve the creation of Earth by a supernatural deity or deities. The Gaia hypothesis, developed in the mid 20th century, compared Earth's environments and life as a single self regulating organism, leading to broad stabilization of the conditions of habitability. You see Tracy Caldwell Dyson and the Cupola module of the International Space Station observing Earth below. Images of Earth taken from space, particularly during the Apollo program, have been credited with altering the way people viewed the planet that they lived on, called the overview effect, emphasizing its beauty, uniqueness, and apparent fragility. In particular, this caused a realization of the scope of effects from human activity on Earth's environment. Enabled by science, particularly Earth observation, humans have started to take action on environmental issues globally, acknowledging the impact of humans and the interconnectedness of Earth's environments. Scientific investigation has resulted in several culturally transformative shifts in people's view of the planet. Initial belief in a flat Earth was gradually displaced in ancient Greece by the idea of a spherical Earth, which was attributed to both philosophers Pythagoras and Parmenides. Earth was generally believed to have been the center of the universe until the 16th century, when scientists first concluded that it was a moving object, one of the planets of the solar system. It was only during the 19th century that geologists realized Earth's age was at least many millions of years. Lord Kelvin used thermodynamics to estimate the age of Earth to be between 20 million and 400 million years in 1864, sparking vigorous debate on the subject. It was only when radioactivity and radioactive dating were discovered in the late 19th and early 20th centuries that a reliable mechanism for determining Earth's age was established, proving the planet to be billions of years old. And that is all for today.